everyone. We're Rob and Alan from the Go team here in New York. And today we're going to talk about a project we've been working on for the last year. But more specifically, we're going to look at what we've worked on for the past 6 months when we drastically redesigned the core of Gopls to scale a lot better and reduce memory usage. I should caveat that this has been quite a sprint, but we're really excited to have released Gopls v0.12 last week, and we're pretty happy with the results, but there's still more work to do. So what is Gopls? Gopls, which is pictured here finding some references, is the engine behind VS Code and other editors that helps them understand Go code. For those of you who use Gopls, you may be interested to know a bit more about what goes on behind the scenes, and we'll talk about that today. And if you don't use Gopls, that's okay too. There are some general ideas here about the construction and analysis of Go programs that you might find interesting. But I will suggest that perhaps you give Gopls a try if you haven't. It's come a long way, and we'd love to know what does and doesn't work for you. But actually, in my very first conversation today, I was reminded that there's a third group of people, and those are the people who have never heard of Gopls, but are using it behind the scenes of their text editor without knowing. And we love that, actually. In fact, that's our goal. So in some sense, our work over the past year has all been about increasing the size of that group, finding fewer developers who have to know about Gopls. But today we're going to talk about what Gopls is and why it's had problems scaling to large code bases. Then we'll discuss how we adapted techniques from compilers and build systems to change the way Gopls scales, and finally we'll share some results. But first, a little bit about language servers. So traditional IDE combines two things, a text editor and a system for analyzing code in a particular language. But it's a lot of work, and there are a lot of languages out there and a lot of editor projects that want to support development in those languages. So in recent years, VS Code took the approach of separating these functions using a common protocol. And that protocol is the Language Server Protocol, or LSP. And at this point, all the major editors have an LSP client. So the LSP allows editors to send requests for things like autocompletion, or jump to definition, or find references to a server program running on the same machine that understands the language. So in some sense, that server program, which we call a language server, is a headless IDE. And Gopls is a language server for Go, maintained by the Go tools team here in New York. That's us. And historically, it unified a suite of earlier tools for analysis and refactoring. So in the olden days, you would ask, say, GoDoc for hover content, and GoFumped for formatting, and GoDef for jump to definition, and Guru for cross-references. The list goes on and on. And around the time that all these tools needed to be updated with module support, the Go team decided it was time to write a language server. Actually, Rebecca Stambler, former teammate of ours, has a great GopherCon talk called Go, Please Stop Breaking My Editor, which describes more of this story. But since we're going to get into some of the nitty-gritty details later, it's worth stepping back and asking, how does any of this stuff work anyway? And so I'll give a super brief overview. In order to understand Go programs, there's a standard process that almost all tools use. They load package definitions using some build system, such as the Go command, and then they parse the resulting files and they type check them. The result is what we call a type checked package, or sometimes just a package. And this is an in-memory data structure that can be used to navigate syntax and query type information. We sometimes refer to this as typed syntax. And this is essentially a compiler front end. In fact, Go is somewhat unique in that its standard library exposes all of these building blocks via the Go parser, Go AST, and Go types packages. So revisiting Gopls, by combining all those older tools into a single stateful process, Gopls initially offered some pretty significant performance improvements. And as a Go user at the time outside of Google, before I had taken Alan's seat, I distinctly remember how fast Gopls felt the first time I used it. But I was working on a relatively small code base, and over time, it became apparent that Gopls wasn't scaling well to large repositories. Here's an amazing quote from an incredibly patient user who is trying to work on Kubernetes. And they were reporting that it took Gopls a minute to become usable after startup. And it's quotes like these that make me love working in the Go community. Of course, understandably, some of our users were less patient. For some reason, I keep coming back to this quote. The first one is what motivates me, I should say. We received dozens of issues reporting performance problems. And by far, the most commonly reported problem was memory usage, which is what this user was referring to. The problem was that those earlier tools that Gopls evolved out of were essentially batch-oriented, which means they performed their operations on monolithic data structures. And these data structures scaled with the size of the code base, and in large repositories, this simply wasn't feasible. We had a big data problem, but not the fun kind of big data problem. And so as we started working on investigating scaling over a year ago, we knew we needed to focus on making this big data smaller. As our earlier user reported, Kubernetes pushed Gopls to its limits, so we used it as one of our benchmark repos. We specifically looked at a few key metrics related to Gopls' internal data structures. The first is startup latency, and that's how long it takes Gopls to fully analyze your workspace after you open your editor. And for Kubernetes, this takes 20 seconds, which is a long time, especially for short-lived editing sessions as are common in Vim or Emacs. And you may note that in the quote 2 slides ago or 3 slides ago, our user was reporting 1 minute here. So I'll caveat that all these numbers were computed on my relatively powerful work desktop. And on an underpowered laptop, you could they could easily be much worse. The next metric is steady state memory, and this is how much memory Gopls requires to be ready to respond to requests. And for Kubernetes, this is around 3 gigabytes, which is a pretty significant chunk of system resources. And finally, there's something we call post-keystroke latency, and this one's a little harder to explain, but it's essentially bookkeeping time. How long it takes Gopls to figure out everything that's changed after you press a key, quite literally. And notably, this isn't the time it takes to provide you with autocompletion results or find references. This is just bookkeeping. And 50 seconds is a really long time. It's actually dangerously close to typing speed. And so in previous versions of Gopls, you can make it fall behind by just mashing on your keyboard for a while. So these metrics gave a pretty clear and pretty grim picture of Gopls' internal data structures, how long they took to assemble, how large they were, and how much work it took to keep track of changes to them. But I will mention 2 other important metrics, not necessarily related to memory, but that we should keep track of. Is there a question? Query latency is how long it takes to actually perform those user-requested operations, such as autocompletion or finding references. And this is actually pretty good, even for large repositories, because, of course, everything was in memory. And then total CPU is effectively battery drain. And unfortunately, with all this bookkeeping and invalidation and corresponding garbage collection, it was pretty bad. But Kubernetes, despite pushing Gopls to its limits, is only arguably a medium-sized repository. It's a pretty large open source repo, but there are larger. So we looked at a number of different repositories, and here's one, the Google Cloud Libraries for Go, which is a collection of, I think, 145 modules unified by a go.work file. And these numbers are even worse. I mean, like 2 minutes, you could take a shower. I could take a shower. I take really fast showers. And now I have less time to take showers, so if I smell today, I apologize. So yeah, this is bad. But people, what always amazes me is how patient our users are. People were using Gopls in this repository. And we heard stories, speaking of patient users, we heard stories of significantly larger corporate monorepos. We heard reports of 17 gigabytes, I'll mention that again later, 24 gigabytes, and someone on the issue tracker was reporting 34 gigabytes of memory usage. But I'm just going to put all those down as infinity because I'm not that patient. That'd be a really long shower. So today, we're going to talk mostly about the first 2 metrics. Why did it take Gopls so long to assemble its internal data structures? And why were they so huge? So this is where we start to get into the details a little bit. So I'll try to give a gist of what these are saying, but you don't have to sort of follow everything. The short answer for why Gopl use so much memory is that it was like it was compiling everything in your workspace simultaneously. In Go, the units of work are packages, and here's a picture that we'll refer to a lot. This is a directed acyclic graph of packages where the edges between circles here are imports. And so in this case, the arrow points from A to B because A imports B. So each package defines a set of symbols such as imported package names, constants, variables, types, and functions. And Gopl was built on a set of compiler-oriented libraries that implement something called symbolic programming, which is where you have exactly one data structure per symbol, and all the references to it are pointers. Like the names of these things don't matter. So Gopl you compare references by comparing pointer identity. That's what those little pointer-looking things represents. So Gopl assembled its knowledge of your program through a large, tightly interconnected web of pointers. And in order to forget even one node in this graph, we'd have to drastically redesign this model. So as we started to think more about this problem, we realized that it was important for us to work backward. Not all LSP operations are the same. Some of them, like workspace symbols or finding implementations, by definition have to search the entire workspace, quote unquote globally. But others, like hover or jump to definition, only need local information about the package that's being edited. And some, like diagnostics, run on every keystroke, while others, like renaming, are triggered only by user actions. And so previously, we didn't have to think about any of this because all of these requests would be handled by the same monolithic data structure. But if we're trying to break this structure, we have to reconsider each of these operations independently, redesigning them so that they can be expressed in terms of incremental, separable actions. What I just said is a little hard to explain in the abstract. So let's take a concrete example of a fundamental operation, finding references to the identifier under the cursor. This is actually a good case study because the references algorithm, as you'll see, is really simple, yet it demonstrates a lot of the problems we were facing. So let's look at that references algorithm. And we'll follow along with this example as we apply improvements later on in the talk. But think of this like a picture book. We'll show some pseudocode on the left, but feel free just to look at the pictures on the right. So in this case, suppose we're editing a package named A, and we want to find references to the identifier under the cursor. With a monolithic graph of packages, this algorithm is dead simple. First, we find the declaration for the identifier under the cursor, and this may be in another package. So in the picture, suppose this is package B. So we found declarations to say b.b, and now we want to find everything that uses that reference. So remember that arrows point away from the package that does the importing. So next, we need to consider all the importers of the declaring package. And notably, because we have to look at transitive importers, because in Go, it's possible to use a field or method declared in another package without explicitly importing that package. In this picture, this is all of the packages highlighted in blue. And then finally, we need to look at all the referring identifiers in the transitive importers to see which point to the target symbol. And here you can see that we're comparing symbols by equality. That's what I meant by symbolic programming. This is symbolic programming in action. And that's really it. I mean, this is obviously a simplification, but it's not that much of a simplification. So how can we improve this algorithm? Well, a key observation for us was how Gopl was like a monolithic build system. And so if we're going to leverage, so what we're going to do is leverage three techniques that help compilers and build systems scale. We're going to separate compilation units, index pre-computed results, and then incrementally rebuild with fine-grained invalidation. We'll explain what all of that means. So first of all, if we want to avoid holding all these complex data structures in memory at once, we need to solve the pointer problem. And it turns out there's a standard technique for doing this, and it's not new. Since the 1950s, people have wanted to compile programs that were too big to be held in memory all at once, and their solution was to break the program into units and compile them separately. This picture is an IBM 704, which is the first real mainframe, and its Fortran 2 implementation was the first to pioneer this concept. But back then, it was the programmer's responsibility to make sure that all the parts of the program were consistent. So if there was a variable v in one part of the program that was an integer, all the other parts had better treat it as an integer as well. It wasn't until much later, in the 1970s, that compilers would export a summary of what they learned from one unit when processing the next unit. And that way, consistent type information could propagate upwards through compilation, upwards through that graph that we were just looking at. And that's exactly what Go does. The compiler admits type information in the form of export data. So our first step was to apply this technique to Gopls, and rather than reusing the same representations of symbols throughout, each package gets a summary of its imports and builds its own view of their exported symbols. And fortunately, we were able to reuse an export data format used by the Go compiler. So let's revisit our case study to see what it looks like now. So using export data means that we can type check each package independently. But then we no longer have a pointer relationship between symbols. In this picture, the data structure representing a symbol in B, when we type check B, won't necessarily be the same exact data structure that we see when we type check A. So we can't compare pointers. Instead, we need a naming scheme. And for this, we'll use something called an object path, which can describe any package level symbol with a string, any exported symbol with a string. So object paths turned out to be pretty fundamental. Let's explain them a bit more. In this example, we're constructing the object path of the X field. And the object path algorithm identifies it as the first field of the second result of the first method of the underlying type of the name T. Of course, that doesn't really matter. The point is that an object path is a stable name for a symbol relative to a package. And unlike pointers, these names retain their meaning even when passed between processes. So success, right? Now we no longer have our monolithic data structure. We've broken it up into little pieces. And so theoretically, now we no longer need to hold all those packages in memory. Unfortunately, no, because type checking is way too slow to do on demand. So until we solve that problem, well, we still need everything. We need some way to fetch references that doesn't involve type checking. Something like a query engine, something like a database. So we need indexing, fundamentally. Turning back to our case study, if we can store a pre-computed index of references for each package, we can avoid scanning the type check package entirely and drop it from memory. In our algorithm, we can check for the existence of an index. If we index the package, we can do a simple lookup. And then the next step is to only type check on demand. If we have an index available, no need to even produce the type check package at all. And yeah, we don't. Pretty simple algorithm. We just do this by first considering only package IDs, not the actual type check package. And we always have all package IDs in memory because every Gopl session starts with a call to go list to list package information. So in this picture, suppose we were editing the package A and we just typed a key. That would invalidate all of the things above A, and so it would invalidate their indexes. But all of the packages on the right-hand side haven't changed, and so we can just reuse their indexes without retype checking. But you might wonder, what if there are no indexes, such as the first time we open up the project? Won't we just generate into the original algorithm and use just as much memory as before? The answer is yes, sort of. If this package is indeed imported by every package in the workspace and there's no indexes, we have to type check everything. There's no getting around that. And the typical way to do that from top down, doing a depth first search, does result in a high peak memory where we just type check everything and then we compute references. But we can do better because we no longer have to ever hold all the packages in memory at once. And I'm going to get a bit hand-wavy here, but basically by doing a top-down pre-traversal, we can figure out exactly what we need, and then we can actually execute our references algorithm interleaved with type checking as we type check from the bottom up. And as a nice side effect, this reduces the total amount of work we do because we play more nicely with the garbage collector. The garbage collector has less to do because there's less heap. For completeness, here's what that looks like in our case study. In our pre-order traversal, we check to see if we already have an index, and in our post-order traversal, as we go back up, we do the slow path if necessary. So in some sense, this is like an optimized, we've optimized our references algorithm. We compute references as fast as possible using as little memory as possible. But of course, we're missing some major pieces. What is that index, and what about recomputing things when state changes? And I'm going to hand off to Alan to talk about these questions.
Thanks, Rob.
Yeah.
So let's talk about the index that Rob mentioned. As Rob said, the references index for the package, if it exists, allows us to look up any symbol by its object path, its stable name, and get the list of locations that refer to it from that package. And therefore, it saves us the need to type check the package, which is the slow path. So what does that index look like, and where does it live? So the code here, on the Go code here, refers to 3 symbols from other packages. We have font_print, we have os.out, and we have the write string method of os.file. And for each reference, just after we've type checked this package, we're going to record 4 pieces of information. We're going to record the start and the end location of the reference, and each of those is a triple file line column. And we're going to record the path of the package that defines the symbol, like font, os, and so on. And we're going to record the object path, the stable name of the symbol within its package. And I've fudged the one for write string here because it's too geeky otherwise, but you get the idea. And by the way, we don't need to bother recording any of the internal references within a package, because we're always going to have to type check one package, which is the one that has the declaration itself. And so we can read the internal references from the type checker data structures for that one package. So we only need this for the cross-package references. So the goal here is that we're avoiding the need to type check all the other packages in the system. So we gather up the references, and now we have a set of 4 tuples. I've shown it down here. And that relation, that set of tuples, is the reference index. Now, obviously, many of the tuples are going to have common fields, like there may be many calls to font_print within a single file. And many of those locations are going to have the same file name over and over again. And so there's lots of redundancy in there, and we kind of squash a lot of that away. So the actual representation is a little bit smarter, but that's just a detail. And I think there's probably still a lot of room for us to improve here. But anyway, these relations become binary blobs, and that is what becomes the index. And the graph at the top right shows the sort of distribution of sizes. Mostly they're very small. There's a few huge ones. This is kind of the normal graph for all of these data structures in this field. So I'm going to show you another one now. So that was the reference index. This one is the method set index. As you all know, in Go, there's no explicit relationship between a concrete type and the interface that it implements. So any type that has a string method is a font stringer, and any type with a read method is an IO reader. So when you ask your editor which concrete types satisfy this interface, or the inverse question, which interfaces does this concrete type satisfy, Gopl is going to need to perform a bunch of subset tests between the interface type and then the candidate types, of which there actually could be a large number because they could come from anywhere in the project, not just in the dependencies. So there's going to be a lot of subset tests here for these methods. So again, during type checking, just after we've built the type checker data structures, we build this index of method sets for each type in a similar sort of a way. So for each type, we record the location of its definition, and we record a set of 4 tuples, each one representing one of its methods. So for each method, we have the position, the fingerprint, which I'll explain in a moment, and then the package path and the object path, which is where is the declaration of that method, or what is the name of that method, really. Now, the fingerprint is a canonical string representation of the name and the type of a method. And it has a very special property, which is that if 2 fingerprints are equal, then the methods are identical in the Go type system. And this lets us implement the interface satisfaction check without building the type checker data structures that we would normally use in the old way. So it lets us just use string comparisons at the lookup time. Now, in most cases, the fingerprints are pretty ordinary strings, like these things here. They look like the way you would sort of naturally print the method name with this type. But in some cases, the more obscure cases, they get more complicated. But we don't have any right here. The indexes that we produce, the distribution of sizes is very similar to the other one I just showed you. It's about twice as big, but again, I think we can make both of these smaller. So where do these indexes get saved, these binary blobs? The answer, in short, is in the file system. And this slide shows the API of Gopl's internal file cache package. It's just about the simplest imaginable persistent key value store, and it only has 2 methods, set and get. And like a build system, the cache records facts of the form, if you follow this recipe, you get this cake. Both the recipe and the cake can be quite large in this case, hundreds of kilobytes in the worst case. And so we use a cryptographic hash to compress the recipe down to a small fixed size thing, 32 bytes. The kind string you see here, which is bake at the top or math at the bottom, is just a way of partitioning the cache for different kinds of purposes so they don't tread on each other's toes. By the way, I couldn't find a flour emoji, so this is going to be a flourless chocolate cake. So as soon as you know the recipe for one of these operations, you call a get method on the cache. Now, if someone's already baked that exact cake before, that recipe before, you get the cake that they made last time. But if not, or if the recipe or the ingredients have changed by even a single bit, then your SHA hash is going to change, and you're going to make a cache miss. Now it becomes your responsibility to do the actual computation, and once you've finished, you write set to put the value you computed back into the cache, so the next time you make a cache hit. A recipe, I'm using this abstraction of a recipe, but it's really just some kind of functional operation plus its arguments. So here's a very concrete one. Factorize this long number, and the result might be the pair of primes that multiply to produce it. A more realistic example in our domain might be compute type information for a package that has these source files, each one identified by its SHA content hash, and these dependencies, each one of them identified again by the recipe hash of that dependency. And so in that way, you can recursively express the entire set of dependencies in a single recipe. That means you're not going to make a spurious cache hit. Like a database, the interface to this package is atomic. So if two threads race, one of them will win, one will lose, but you'll get definitely one answer, not a mixture of the two. And note that it's also not a content addressable store. The key is the hash of the recipe, not the cake. Otherwise, you wouldn't be able to do make a cache hit without baking the cake, which would sort of defeat the point of having a cache. I'm going to show you now just a little bit about the implementation. It's a global persistent store, so it lives on your machine. There's one directory in your machine that holds all this stuff. Set and get really are global functions, not methods on an object. And the cache lives across process restarts, and it handles multi-process concurrency. So in other words, you can run two Gopl sessions at the same time, you can restart your machine, and it's always accessing the same cache. Now, a little bit about the structure of the file name. The kind and the key pair become part of the name of this file in this directory. And basically, it's just put somewhere in the system's per user cache that we've reserved a part of the namespace with the string go please. That's how we take it from other applications on the machine. And then this is an important part here. We actually encode the hash of the go please executable as a segment of the directory of the path, so that any change to the go please itself, any of its algorithms, will cause us to use a new cache. And that's very important for correctness, because even the tiniest change to the logic could actually invalidate all of the things that we've written to the cache already. You can think of this as the hash of the kitchen and all the appliances in the kitchen. And every cook knows that every oven has its own unique personality. And then finally, the key just forms the last part of the file name. If you're curious, you can run this command at the bottom. It's a new command, go please stats, that tells you, among other things, where to find this cache. And we use a garbage collector to limit the size of the cache to about 1 or 2 gigabytes, and files no more than about 5 days old, and that seems to work well. So I'm going to tell you now just a little bit of a digression, a sort of sidebar on how we update the cache, because I think it's actually a valuable lesson here. So we have multiple processes trying to write concurrently to a cache. How do we make sure that it's atomic? And the classic Unix answer to this is to use the rename system call, which guarantees that the rename either succeeds or fails, but it won't leave you with nothing or a mixture of two things. It's always atomic. And so this works beautifully on Linux, works well on Darwin, but it simply doesn't work on Windows. Windows has no way to atomically rename a file even within a single directory. It has lots of things that look like they should work, but none of them work. It really doesn't work at all. So nope. So the second attempt is how to do an atomic update without renaming. What about file locking? That sounds like the name is a good promising clue. And every operating system and file system has some kind of locking system calls, but unfortunately, it's always been a notoriously buggy and unreliable and unportable set of system calls in every system. And so we spent a lot of time experimenting with this, 3 different implementations for various systems, and it was just too buggy. All our tests would keep giving flakes. And ultimately, we decided file locking was not working for us, which kind of should not have been surprising, because we sort of knew that file locking never really worked well for anyone. And then I had a conversation with Russ Cox, who pointed me at a simpler and more reliable solution that he had designed for the cache used by GoBuild since around 2018. He observed that although no file system guarantees that concurrent file writes are atomic, every file system does in fact behave that way, and must, for internal reasons, behave that way for small writes. And I'm talking about small meaning less than the size of a disk block, which is about ½ a kilobyte conservatively. And so the trick is to introduce a level of indirection. The file contents, the cake, gets saved in a content addressable store, or CAS. That means that the name of the file is the SHA hash of the content of the file. Now, if such a file already exists, then there's nothing to do. We just check that the contents match as they should, and then we don't need to overwrite it. But if we were to overwrite it concurrently with another thread, that would be totally safe, because we're writing the same thing as that other thread. Once the CAS file exists, the main file is just the name of that CAS file. It's just the hash of that file. And so you can think of it as a bit like a symbolic link. And that name is only a 32-byte string, and so it's a very small file itself, and therefore it's safe to assume that it can be updated atomically, and that's what we do. There's no way that you can actually observe those 32 bytes in the middle of being written. And what's really interesting here is, and the read function does, I won't go into it, but does the analogous thing of read the link and then read the main file. The interesting thing is that this approach actually relies on undefined behavior on every platform. It's like officially totally non-portable, and yet it's actually 100% reliable. It's been used for 7 years in the Go command, not a single bug report. One last detail is that we put 100 megabyte RAM-based cache on top of the file cache, so that most of the time you're not actually even hitting the file system. And that made quite a big difference to performance. So many of you in the audience are probably thinking, like, you just invented a crap database. And we did. So why didn't we reuse an existing database or key value store? Because they've already solved the problems of debugging, performance, portability, and many other things. And it's a really good question. And I'm sure these tools are all really good at this job. However, and probably even faster than our implementation, because modern databases are faster than reading and writing the local file system for small operations. But the reason is that we in the golang.org/x repos are extremely strict about dependencies, and databases are generally very large dependencies, and so we just couldn't really go there. But I want to emphasize that the actual solution we did was really simple. It was less than 100 lines of code for the whole thing. So it was a really good solution for us. And if you need a small local key value store, you might want to try this yourself. So now that we've covered the file cache, let's go back to the idea of Gopls as an incremental build system. So what happens when a change comes in? If you look at the yellow node, this yellow package, we don't need to invalidate and recompute every single node in the graph just because that one changed. Only the upward dependencies of the change. And this is not a new observation. This is what we mean by an incremental build. It's what Make did in the 1970s and every build system since then. Now Make uses timestamps. It wants to keep the invariant that newer things point to older things. And so if the yellow node has changed, then there's work to be done to recompute the purple ones above to make them newer. And if you change the yellow node again back to the way it was, then you still have to recompute everything above it again to make sure that it's newer than the second change. And Gopls has always done this too, the equivalent of an incremental build. In Gopls 011, when we replace the yellow node, we have to recreate all the purple nodes with their downwards pointing pointers. And since those objects were created more recently, their kind of timestamps are newer, even though we don't actually really care about time in that program. But newer build systems don't actually work this way. Vesta in the mid-1990s had a new idea that we used in Bazel, which I worked on at Google in the early 2000s, and it's used in GoBuild since 2017. They don't use timestamps. They don't blindly throw away old work just because one of the dependencies became newer. Instead, they ask, have we done this requested task before? Have we baked this recipe? So consider a small local change to a package, like the addition of a print statement. Clearly, the yellow node needs to be recomputed, but what about the packages above it? Their source files haven't changed, nor is the summary of the type export data that's passed upwards from A, because the change didn't actually affect any of A's exported types. So when we look at the nodes above A, we can make cache hits because the recipe is the same as before. The key thing is that if you can define the recipe precisely without the irrelevant ingredients that you don't actually need, then you're able to make cache hits when only the irrelevant parts change. And a fun fact, if we were to actually revert this change, delete the print statement, we would actually make another cache hit because we've returned to an old recipe that's still in the cache. And you've probably noticed this when you're using Go test. You run the tests, you make a change, and you test again, and then you revert the change, and you test again, and the tool says, aha, that's actually a cached test. We've already done that before because it's reverting to a previous state that's in the cache. Another fun fact is that inserting a print statement isn't always a local change. If there was a declaration below there that was exported, its line number would have changed, and that could affect error messages, and so we have to account for that in the export data. So now let's consider a more substantial change to A, like changing the signature of the function. In this case, we're adding a string parameter. This time, the summary of types exported from A has actually changed, and so all the nodes above are invalidated and are recomputed. But still, the reach of this change is actually fairly local. You can only call the function a.a if you import package A directly. So the only nodes that really need to be recomputed are those directly above A. The indirect importers can't be affected. So let's see another example where the invalidation is more than necessary. Here's an even more substantial change to A. We've added an exported field to an exported struct. Surely every node above A in the graph can be affected by this change. Well, potentially, but let's look at B. B uses a.a, the function a.a, only internally. It doesn't export, the type a.a, only internally. It doesn't export any type information about A in its own API. And that means we know that package C cannot possibly be affected by this change. So this is the beginning of an idea. What if for every package we could compute the subset of its forward dependencies whose summary, whose type export data could possibly affect it? And that's the basis of an optimization that we call fine-grained invalidation. And I'm only going to have time to give you a little flavor of the algorithm here. But the basic idea is that we look at each package's syntax trees, and I'm using this rectangle here to represent the fumped package, and we build this structure that represents the path through the package from its public API, like printf and scanf, to the things that it depends on, like strconf, parsefloat, and so on. And we're following, in building this path, a kind of chain of references from one function to another function through a type and so on. We actually don't need type information to do this. We're just following the syntax trees. So this is important because it means that it's just a property of the syntax of the package itself, not of its dependencies. And that means we can save that information just keyed by the syntax itself and not by anything to do with the dependencies. Well, that does mean, because we don't have type information, that we have to make some conservative approximations. So here's the structure that we got from the funct package. You'll notice that printf and fprintf are very similar, and they kind of go through this huge blob of shared printing code. And that blob needs a couple functions from strconv and errors.new and so on. And scanning is a different blob of code with different requirements of other packages. And so it needs different imported symbols. So then we use a bunch of graph algorithms to kind of pull these strings straight to find all the shortcuts through these packages. And that gives us kind of a compact summary of each of the dependencies of a package at a very fine grain. We call it the symbol reference graph. And we can save this information in the cache and invalidate it one package at a time without worrying about other packages. So now how do we use this? Now look at the main program over here. Let's consider that it calls log print, and then the sync package in yellow here has changed. So the sync package, it looks like naively everything above the sync package is invalid, right? We have to get rid of funct and log and main and recompute those. But actually we can see, if we stack up these blocks and link the kind of paths together, we can see that there's no fine-grained path from main that reaches the sync package. And so we know there's nothing that could change in sync that would cause us to have to invalidate main. So that's the kind of the basic idea. And this greatly reduces the amount of work that we have to do after a change to a low-level package. And so Rob's now going to show you the numbers.
Thanks, Alan. So we're pretty excited about the results. As you can see, I just realized you can see that we're working on a blog post, so you can also see the results there. So we've described a lot of work. We've focused on the references algorithm, but we applied a similar process to almost every operation offered by Gopls, so that we never had to use that monolithic web of pointers that was so problematic. And going into this process, we were working from first principles. So we must avoid holding things in memory, which means we have to name them and index them, and then we should avoid recomputing those indexes whenever possible. And so we expected this to improve our scaling. We had an idea of what to expect, but we really couldn't be sure of what our results would be. So after all this work, what was the result? So thankfully, things got a lot better. And let's revisit those key metrics. With the new design, as Alan described, Gopls persists data in a file cache across sessions. And as a result, the second time you open a repository, startup time is much faster. So these numbers here are startup timings for the second time, but even the first time got faster because of the optimized type checking that I described. And I should note that a big chunk of this improvement is also due to improvement in the Go command, which benefits everything, thanks to Michael Matlub. So great, so now I only have 12 seconds for my shower. And so steady state memory is down up to about 800 megabytes for both both Kubernetes and Google Cloud Go. There's reasons for why they both have the same number. But essentially all we keep around now are file contents and some data structures to optimize the type checking of whatever packages you have open. I think we actually do a lot better here because for things in the module cache, the Go command provides guarantees of consistent reads. So we could actually drop everything from the module cache as well. And we didn't talk about it today, but we also worked on improving our bookkeeping using immutable copy on write data structures, and we got those numbers way down. And what about those other metrics, query latency and total CPU? Well, so query latency is still pretty good. In fact, so it was good before, and our goal through this whole project was not to make it too much worse. It actually got better in a few areas because index lookups are faster, and it got worse in others. I mean, generally speaking, slow operations got a little faster, and fast operations got a little slower. And total CPU got a bit better, again, because of the improved invalidation, but we still have more room for improvement. In particular, because we've broken up this monolithic data structure, we have some options to trade CPU for freshness. But you may be thinking to yourself, didn't you say 10x on that first slide? All those numbers look like 4 or 5x. And so, yeah, that was a bit of a lie, but not perhaps in the way that it may seem. So our goal wasn't actually any x. We didn't want to reduce memory by any constant factor. We wanted to change the asymptotic behavior of how Gopls scales. And you can see here that, in this graph, as you go to the right, the repositories get larger, approximately linearly. And you can see here that we have achieved a sublinear scaling, which means the ratio of reduction goes up as the repo gets larger. And that 17 gigabyte monorepo that I alluded to early on in the talk was DigitalOcean's. Billy Cleek, who's the maintainer of Vimgo, had reported that. And Billy followed up after our V12 release to report that they were down to 1.5 gigabytes from 17 gigabytes. So that's pretty great. That's an 11x savings. And so there's your 10x. So yeah, we're really happy with that. So we have lots of ideas for future optimizations, but we're excited for your feedback today. Please try out the latest version of Gopl and let us know what you think. And thank you for listening and bearing with us through this rather technical talk. We hope you got some interesting things from it, and we hope that you try out the latest version of Gopl. And I also want to say thank you to all of our teammates who supported this project and the external contributors, the community contributors who helped out along the way. So thank you.